So, hi, my name is Saul, and this is Franklin. And as he said, we're going to be talking about adopting data frames in Parquet in an already existing warehouse. So about a year ago, all of our data was in JSON format, and we were running RDDs. And now all of our data is in Parquet, and we're starting to adopt data frames. And this is generally a story about what it is that we did and why we made those decisions. So to start off with, we both work for Shopify, so that's the data warehouse that we're going to be talking about. And we're just going to first explain what it is that our company does, and that'll give you an idea about the data that is inside of that warehouse, and that should help explain some of the stuff we did. So to begin with, we're not Spotify. We often get confused with Spotify, but they're a music streaming service. We are Shopify. We're a store hosting service, so our data is very different. We deal with online stores. So if you were to actually sign up and create an account, then this is the first thing that you would see, and you would see on the left there that the first thing you would want to do is add products to the website. So once you have products that are in the system and we're able to track all of your inventory, then the next thing you'd want to do is to create a custom website to your look and feel, and that way you can start selling stuff online. We also provide point-of-sale services, and you could also sell stuff on Facebook. So once you have a sale, then you're going to want to make sure that your order ends up getting fulfilled. So that's another source of data, tracking orders. And then also, now that you've sold something, you have a customer. So you're going to want to also track your customers so that you could have repeat sales, and that's great. At the end of the day, you might want to know how much you sold. So that could be a report. Another one is how much you should be paying in taxes at the end of the year. That's another kind of interesting thing. So we keep all of that data, and that's all displayed to our users. And then internally, we also have data on all of this. So we look a lot like a business warehouse of a whole bunch of different businesses. And internally, we also want to have a marketing team, and we also have 24/7 support. We want anyone who calls us to have a positive interaction and get the knowledge they want. So that should give you an idea of the kind of data that is inside of our warehouse. And this is a single warehouse, and it is entirely powered by Spark. So we're a Python shop, so we generally use Pyspark. And that's kind of like an artist's depiction of what it looked like. Our data generally comes in through MySQL, sometimes Kafka, and HTTP APIs as well. And what we used to do was we would store it on HDFS in JSON format. So the reason we decided to go with JSON was mainly because this was our first time working with HDFS, and we didn't really know what file type to go with, so we generally decided not to decide. So everything works with JSON, no matter how badly, and that was okay with us, because then we don't actually have to be locked into some sort of thing that we didn't necessarily want. So once the data was on HDFS, then we would pick it up, and then we would do all sorts of transformations, clean the data, and if it was to be displayed to our user, we would then put it into an operational DB, which it acts kind of like a caching layer or a view so that our users can get a fast view of the data that they want very quickly. And then internally, we also have our own data analyst team, and they would end up using Presto to look at the data inside of our data lake to know what to do. And then once the data was nice and clean, our tier 1 front room is Redshift. So that's where all of our nice data goes for making important business decisions. Okay, so a few factoids about our warehouse. At the moment, we have over 300,000 stores, which are stored inside of this warehouse. That works out to about 2 petabytes of data. We run about 4,000 jobs a day, and we ingest about 1.5 terabytes of new data daily. So we're actually a company that's experiencing hypergrowth. So by this time next year, all of those numbers are expected to double. And that creates a lot of pressure on our warehouse, because it means that by this time next year, we're going to have to process twice the amount of data. And in order for our customers to be happy, that's going to have to be done in the same amount of time. And in order for our financial department to be happy, we're not going to have to, well, we can't just keep doubling our budget every time. That's just, they're not going to like that. So that's the general problems that we're dealing with. And yeah.
So why are we doing this migration? This is a huge undertaking, so we better have a really good motivation for doing it. So as good as the architecture diagram that we saw looked, this is kind of what it started to feel like on a day-to-day basis. We started to see some of the cracks in our early architectural decisions. Mainly around JSON that we're storing in gzipped JSON blobs, which are unsplittable, so it's really hard to parallelize it. Also around RDDs, we're using the PySpark API, which means that the majority of our data processing is happening in the Python VM, which is a lot slower than the JVM. So we're seeing huge processing times and delays to getting our jobs output onto HDFS. So our business consumers weren't happy. And we're also seeing huge development and iteration times. So our data analysts were writing queries against HDFS, and generally we were seeing that they were spending more time waiting for the results to come back than actually modeling data and actually being efficient. So these two things combined added a lot of cost overhead. We were spending a lot on infrastructure because our processing times were so slow, and our developers weren't being efficient, so they weren't doing the job we were paying them for. So we decided we need to reevaluate some of our architectural decisions. So we landed up on Parquet and Dataframes. We're using Parquet because it's a columnar format, so we get some cool Spark optimizations like predicate pushdowns and column projections, so our jobs can pick up just the columns that they need for their execution. And like I said, we're on the PySpark API, and the reason we chose the PySpark API is because it's really familiar to data scientists. So it's really easy to hire a data scientist who is familiar with Python. And the PySpark API is just really easy to pick up and get going. So we wanted to maintain all that Python simplicity, but we wanted the JVM performance. So we decided to go with Dataframes, because you can still compose all our jobs in Python, but we offload our computation to the JVM. And lastly, we wanted to be able to run SQL queries against HDFS. This was something that was just really slow in our legacy, like JSON and RDD API. So we couldn't really use SQL to do data analysis. So we came up with these goals. First and foremost, we decided that while we were doing this migration, we're going to be picking up a lot of data and converting it over to Parquet. We don't want any of our consumers to actually notice what we're doing. So we're going to do this migration without any downtime for our business consumers. So everyone who needs data on a day-to-day basis will still be able to access it. We also want to remain full backwards compatibility. So we have a huge code base of JSON and RDD jobs, and these need to continue to work as we're doing this migration, regardless of the changes we're making to the code base or the data format. We also want to incur no data loss or corruption while doing this. We're on a data warehouse. The trust in our data is absolutely paramount. And we want to maintain that trust as we go along. We don't want any of our business users to be able to question a report or some kind of statistic that we've generated, because we want all of our business users, both internal and external, to be able to make data-driven decisions. And lastly, we wanted to do this migration incrementally, which basically means we're going to take small incremental steps, make checks along the way. And this mitigates a lot of risks in making a huge migration like this. Because you take a small step if something doesn't work out. If we have a data integrity issue, we can always take a step back to a safe spot. So our adoption plan was to first start off by keeping all our old code. What this means is that basically we have this huge legacy data modeling framework, and we're going to try as much as possible to reuse all the code we have. So if we can reuse code between the RDD side and the Dataframe side, we're going to do that. So this means that wherever we see that we have to use different behavior for RDDs or data frames, we're going to introduce a new code path for the data frame side. Or similarly, if there's something different between JSON and Parquet, we're going to introduce a new code path for Parquet. So that's how we're going to bring it in. And then once we've brought in the data frame API, we're going to pick up some of our worst case offenders, like the absolute slowest jobs we have in our warehouse, and we're going to rewrite them using data frames and see what happens. Like, as I mentioned, we want to maintain backwards compatibility. And what this means is that jobs that are running right now, if we switch out Parquet from under them, they should be able to keep running. So in order to do this, we need to build two compatibility layers around our job. One's on the input side and one is on the output side. And what this lets us do is switch out the output format without really changing any of the code inside the job. So on the input side, we have what's called a data agnostic reader. It's a really simple API, really easy for analysts to use. All they have to do is mention where their data is and what kind of data set they want back, and we just give it to them. So they can read either Parquet or JSON as an RDD or a data frame. And it doesn't really matter to their job. On the output side, we have this like tiny blob of metadata. It describes what each job does. And what we did was we added a new field to this metadata called output format Parquet. And this lets us configure the output format of a job really easily just in metadata without changing any code. So in our code base, what this looks like, it's really simple. We just see if the output format is set to JSON or Parquet, and we either write JSON to HDFS or we write Parquet to HDFS. So that's a bit about how we added code paths into our code base. And this is kind of what's happening physically, how we actually move jobs over. So in our data warehouse, we have two different kinds of jobs. The first job is called a full drop job. And what the full drop job does is it picks up all of its inputs and writes out a brand new data set every time. So this guy is a bit easy to migrate over to Parquet. All we had to do is go back to its metadata, switch that output format over to Parquet, and the next time that Spark job spins up, it's going to write its output to Parquet. The second kind of job we have is called an incremental job. This job kind of typically deals with data sets that are too big to pick up all in one go. So it picks up a batch of data and writes out its output. And then when new data comes in, it'll pick up just what it hasn't processed yet and write that out. So for these jobs, they were a little harder to migrate because we can't just switch their output formats to Parquet because then they'll start writing Parquet to an existing JSON output directory. So for these jobs, what we have to do is develop scripts to go into the output directory, pick up all the historically processed JSON, write those out to Parquet, and then we can finally switch their output format over to Parquet. So there's a bit of a coordination issue involved with these kind of jobs because you don't want that job to be running while you're making these changes. Otherwise, you might get into an inconsistent state where your job is writing Parquet to a JSON folder or JSON to a Parquet folder.
Cool. So now that we've talked about how we're going to maintain backwards compatibility, the next step is actually to move forwards with data frames and start writing data frame code. So the first thing we want to do is to make sure that whatever data set we're working with is actually data frameable. As it turns out, that's not always the case. The next thing is, once we have a data set that's theoretically data frameable, we actually want to take the job, write it as a data frame, and make sure that the information that's being written to disk ends up being informationally equivalent to what it was before. So we call that checking data integrity. And the last thing we want to check is something that we call regression blocking. We don't really, maybe it needs a better name, but the main thing is that we keep on getting new employees and they might look at some code and go, oh, what's that? Oh, that's outputting JSON. So I'm going to write a job that ends up outwriting JSON instead of Parquet, or I'm going to write an RDD instead of a data frame job. And at some point, we don't want our users to do that anymore. So we call that regression blocking. We stop them from doing it so that they always go forward with the technology we want. So first things first, will it data frame? So as it turns out, not all types in Python land are the same as their data frame equivalent. The two main ones that we found are pretty different are longs and decimals in Python. So a long in Python is essentially an integer that goes from pretty much negative infinity to positive infinity. It could have pretty much any given size. Whereas when you go to data frames, it gets stored as a SQL long type, which under the hood is essentially a Java long. So it's 64 bits of, it's a 64-bit integer. So it can be from minus 2 to the power of 63 to 2 to the power of 63 minus 1, which is quite a bit smaller than negative infinity and positive infinity, but pragmatically speaking, most of your data will end up fitting in it. And the second type that we noticed was pretty different is the decimal type in Python. So in Python, it ends up being 28 prec, or 28 significant digits, whereas in data frame land, it gets stored as a SQL decimal type 3818. So what that means is that whatever your number is, it's allowed up to 38 digits, 20 of which are to the left of the period and 18 to the right. So let's say you had a number like a Google, which is 1 times 10 to the power of 100. That's one significant digit. You're going to end up having 80 of those digits lopped off. And then if you had 1 divided by a Google, then you'd end up having of decimal places 19 to 100 all being lopped off. So you do have to end up checking for that to make sure that you don't have that. So how do you check that? Well, you actually physically have to check it. So what we ended up doing was we picked up all of our data sets and then we looked at every single column. Any column that had a long or a decimal, we would check all of its values. So for the long, we would pick up the value. We would then make sure that it's every value within that column is within the allowable range for going to a SQL long type. And if it was not within that range, we would want to emit that value in some way. That way, we know what the value is that doesn't fit in that range, so that we make a more intelligent decision about what to do next. And we ended up doing the same thing for decimals. So what we did was we created this decimal context which simulated the SQL decimal type. And if you'll notice at the very end, there's that traps in exact. And what that does is it throws a round-off error if there's any sort of round-off when you actually take the value and apply this context to it. So we would wrap it in a try-catch, and if it ends up having any sort of round-off, it throws an error, and then we can look at the value and then make an informed decision about how it is we're going to deal with this sort of round-off error. Maybe it's close enough and it's okay, maybe it's not at all. So that's the first gotcha. The second one that we noticed is something that we're calling like an optional column. So when you're dealing with JSON objects, they're essentially dictionaries, and you could have some fields which are present in some records that are not present in others. So in this example, in the first record, there is the B field that doesn't exist in the first record, but it does exist in the second. And then if you go to a data frame, which is essentially a much more structured data type, so it ends up having a column instead of a field, and that column exists for every single row. So if you'll notice in the first record then, instead of it not existing, it does exist and its value is none. So that can get you a little bit into some hard to debug situations if you're then asking, okay, is this field in the data? So in data frame land, yes, it always exists, but then in RDDs, it could be totally optional, and in which case you'd end up taking a completely different code path, and that could be a lot of problems. So that's something that we used to allow, and we don't allow it anymore. So at the end of the day, if you're writing a job, you really should know what exactly is being written to disk, and you should know if there is some sort of an optional field within it. So what we ended up doing to stop that so that we can move forward with data frames is we no longer allow fields being written that are optional. So we created a whitelist of every single job that writes out some sort of an optional field, and those ones get a pass. And then anytime an analyst tries to write a new job which ends up having some sort of an optional field, we don't allow it. So this test ends up failing, and then they're not allowed to merge that code into production. So then they have to rewrite it so that it no longer has an optional field. And that way, that job is much easier to convert over to Parquet and also much easier to Dataframe.
Right. So as I mentioned, we want to do this whole migration without any data loss or corruption. So we're thinking about how we could do that, and this is kind of what we came up with. So essentially, we have two code paths in our code base. One runs JSON, one runs Parquet. So we can spin up two jobs that take in the same input, and they write out JSON or Parquet. So this kind of tests both code paths, and then what we can do is we write a third job. It picks up the Parquet that's outputted, picks up the JSON that's outputted, and compares them row by row by row, and make sure that they're exactly informationally equivalent. So this was a great pattern, and we used it throughout our entire migration. So this means that whenever we do a big migration, we apply this. So whenever we're converting an existing RDD job over to data frames, we can do it again. We just run them with the same inputs and make sure that the data they're writing out to HDFS is exactly the same. So this became kind of like a hard and fast rule. It's absolutely mandatory to go through this process to do any major migration in our system. And as Saul was mentioning, we want to just keep moving forward with the technology we've introduced. We did a lot of work to convert our data over to Parquet, and we did a lot of work to implement the Dataframe API in our framework. So we want to make sure that there aren't any regressions. So what we did was we scanned our code base, found all the existing jobs that run on JSON or RDDs, and we created a whitelist of them. So we're not going to be able to rewrite all these jobs in one day. Some of them might never be rewritten. So these jobs get a free pass. They're going to stay in our code base for a while. But whenever an analyst checks in a new job, we check it against the whitelist. If it's in the whitelist, that's fine. We'll give you a little extra time. But if it's not on the whitelist, that test fails, and you can't move on. So this kind of draws a line. It stops the bleeding and lets us only move forward with our new work. So we did all these migrations, and what we've been typically seeing is the jobs that we move over to data frames are on average 10 times faster. And it's not that they're just faster, they're also using fewer resources to do their work. And while we were doing these migrations and code rewrites, we found that we kind of had to tune the resources that we were using for these jobs. And that was kind of expected because we know that we're offloading more work to the JVM, so we're going to need more Java memory. And finally, we were able to bring SQL to our analysts, and they were really happy with it because a lot of our analysts are really well versed with SQL, so they prefer to work in a SQL environment and query HDFS that way.
Cool. So lessons learned. The main one that we took away from this is that data frames essentially pay for themselves. We were noticing that on any job we moved over to data frames, we get around, on average, a 10 times performance increase. So what that means is that we're able to run, theoretically, 10 times the number of jobs on the same amount of infrastructure. So that's really good financially, and on top of that, all of our analysts are getting their data at a much faster rate, so they really like that too. So it's been a really big win for us, and we're really happy with it. And the next takeaway is that you don't just wake up one day and go, oh, hey, let's do data frames, and everything's done. Moving to data frames is a big switch. You do have to rewrite your entire RDD job into a data frame job, and if you're moving your data format on disk, you really have to check your data because, well, your data is really important, so you have to do it. So that's the other thing, is that doing this still is a lot of work. There's no magic bullet. And finally, the last thing is safety first. Like, we deal with a lot of data that has to be accurate to the penny, and so if the data ends up being different on disk before or after whatever it is that we're doing, that's a big deal. Someone's going to notice. So at the end of the day, the data is the star of the warehouse, and the technology is more of an implementation detail. So you really have to keep safety first. So thank you for listening. Also, we're hiring. As I mentioned earlier, we're a company in hypergrowth, so by this time next year, there might be 4 of us on stage. That's the website if you're interested. And thank you. We'll be happy to take any questions. Cheers.
So say I am using one of the upstream data set that is in Parquet, but the code is trying to read it as an RDD. Do your system support that use case of converting the RDD back to just, data frame back to just RDD of JSON?
Oh, as in, can you write out JSON?
Yeah, as in, because of for a lot of systems, the downstream system might still write code to process JSON, and some logic are not available to migrate to RDD right away because you write in SQL model now.
Right. Yeah, we do allow for that.
So what's the cost of schema conversion when you try to output a JSON output back to Parquet? Did you experience that, the cost of schema inference?
Oh, as in changing?
Oh, yeah, we don't do any schema inference, so we have fixed schemas for our data.
Okay.
Oh.
Yeah.
You know, one thing that the advantages of data frames is in space savings. Parquet is more compact than JSON. Mm-hmm. You didn't mention you mentioned that the financials were important, any company, of course, but you mentioned that the savings and space, these kind of things. And the second question altogether is this process finished? Is your objective to get rid of JSON, or you expect to get both format JSON and Parquet coexisting in your system?
Sorry, I missed the last part. Yeah.
The second question was that, you do the transition between JSON and Parquet, mm-hmm. But the idea is that to get rid of JSON, or just to get a system which you can deal with JSON and Parquet at the same time?
Right. So the long-term goal is to get rid of all the JSON.
Yeah.
The first question.
The other part was, about the size?
Size.
That isn't as important for us.
Yeah.
Just in general. Yes, it does matter money-wise, but our bigger cost is more just, we keep on having to buy more compute nodes. That's more of our bottleneck as far as pricing right now.
Yeah. Two related questions. So first one, do you partition your data like do you do any kind of partitioning of the Parquet files? And the second one is, do you care about Parquet file sizes? So do you aggregate them together, like to have bigger files? If you will have like smaller files, like Spark might choke on them or something like that.
Oh, as in like how many Parquet files on disk? Like that kind of thing?
No. Do you aggregate small Parquet files to bigger one, just for performance improvement?
Oh, yeah, we do.
And the first question was partitioning Parquet files?
I'm not We do play with partitions, depending on the performance of the job, if that makes sense. So it's more of like, that's more of a tuning kind of thing. So it really depends on the job, how easy we're going to partition it.
Yes, first, thanks for the talk. My question is about, you have got a 10 faster performance with Dataframe, and initially you were starting with Python coding with RDT. About the Dataframe implementation, have you had to rewrite any custom business logic as a UDF from Python to Scala, or have you been able to stay with the SQL syntax to get this improvement in performance?
Yeah, so initially we wrote a lot of Python UDFs because we do have areas where we need to do that, and we found that that incurs a lot of, like, you have to send data back over the Py4j bridge, and it made things really slow. So right now we are implementing our own Scala UDFs to replace that logic. Yeah.
Thanks.
Do you guys use nested structure in your JSON and in your Parquet?
Nested structure? No.
No,
it's flat.
Yeah.
So yeah, that would have been another problem had we done that.
I think there's a question here.
Yeah.
During the talk, you mentioned that your JSON files were like gzip compressed. For the Parquet files, you mentioned that so gzip is not splittable compression. Do you use a new compression with Parquet, or is that a plan? Or?
I think we're thinking about Snappy.
Yeah, I think.
Yeah.
Hey guys, thanks for the speech. It was really interesting. Just one question regarding Parquet. Do you do any research into the Parquet block size you're using?
Into the, sorry?
The Parquet files themselves. Are you using, do you do any modification regarding block sizes of Parquet files, or you're using default parameters?
Yeah, I don't think we've done that, no.
You didn't do any
straight up Parquet
research on that area? Any testing, any? No.
I guess not, no.
Okay, thank you.
Because we're just using straight up Parquet.
That's fine. Thank you, guys.
Okay, if there are no more questions, thank you very much.